Alright, looks like we are live. Okay, let's continue. Okay, in this session, we will take a look at the free space management. Yeah, previously we already take at the chapter 16 here, segmentation, and now we will take a look at the chapter 17, free space management. Alright, let me open that. Okay, free space management. In this chapter, we take a small detour from our discussion of virtualizing memory to discuss a fundamental aspect of any memory management system, whether it be a malloc library managing pages of process heap, or the operating system itself managing portion of the address space of a process. Okay, a fundamental aspect of any memory management system. Okay, specifically, we will discuss the issues surrounding free space management. Alright, now, okay, let us make the problem more specific. Managing free space can certainly be easy, as we will see when we discuss the concept of paging. Okay, it is easy when the space you are managing is divided into fixed size unit. In such a case, you just keep a list of these fixed size units. When a client requests one of them, return the first entry. Okay, it is easy when the space you are managing is divided into fixed size unit. In such a case, you just keep a list of these fixed size units. When a client requests one of them, return the first entry. Where free space management become more difficult and interesting is when the free space you are managing consists of variable size unit. This arises in a user-level memory allocation library, like in malloc, and free, and in an operating system managing physical memory when using segmentation to implement virtual memory. In either case, the problem that exists is known as external fragmentation. The free space gets chopped into little pieces of different size and is thus fragmented. Subsequent requests may fail because there is no single contiguous space that can satisfy the request, even though the total amount of free space exceeds the size of the request. Right. The little piece of different size and is thus fragmented. So there is no single contiguous space That is the problem. Okay, the figures show example of this problem. In this case, the total free space available is 20 bytes. Unfortunately, it is fragmented into two chunks of size 10 each. This one 10 bytes and also 10 bytes. As a result, a request for 15 bytes will fail even though there are 20 bytes free, and thus we arrive at the problem addressed in this chapter. The crux here: how to manage free space. How should free space be managed when satisfying variable size requests? What strategies can be used to minimize fragmentation? Right, minimize fragmentation. What are the time and space overhead of alternate approach? Okay, that is the crux. How to manage free space. Assumption: most of this discussion will focus on the great history of allocator found in user-level memory allocation libraries. We draw on Wilson's excellent survey, but encourage interested reader to go to the source document itself for more details. Let me check the footnote first, I guess. It is nearly 80 pages long, thus you really have to be interested. Oh, 80 pages. Okay. We assume a basic interface such as that provided by malloc and free. Specifically this one. Okay. Take a single parameter size, right? This one with the type size _t, which is the number of bytes requests by the application. It hand back a pointer of no particular type or a void pointer. In C lingo, what lingo means? Is it a programming language? Yeah, I'm not sure what lingo means. C language, maybe something like that. To a region of that size or greater. Oh, or greater. Okay. The complementary routine is free here. Take a pointer and freeze the corresponding chunk. Note the implication of the interface. The user, when freeing the space, does not inform the library of its size. Okay. Note the implication of the interface. The user, when freeing the space, does not inform the library of its size. Thus, the library must be able to figure out how big a chunk of memory is when handed just a pointer to it. We will discuss how to do this a bit later on in the chapter. The user, when freeing the space, does not inform the library of its size. Okay, does not inform the library of its size. Thus, the library must be able to figure out how big a chunk of memory is when handed just a pointer to it. Yeah, that is, what is it called? The interesting part of free function here. How can we determine the size when we just provide the pointer, Okay. And apparently we will discuss that later on in this chapter. The space that this library manages is known historically as the heap, and the generic data structure used to manage free space in the heap is some kind of free list. This structure contains reference to all of the free chunks of space in the managed region of memory. Of course, this data structure need not be a list per se, but just some kind of data structure to track free space, right? The structure does not need to be a list. It just needs to be some kind of data structure to track the free space. Okay, we further assume that primarily we are concerned with external fragmentation as described above. Allocator could of course also have the problem of internal fragmentation. If an allocator hands out chunk of memory bigger than that request, any unasked for and thus unused space in such a chunk is considered internal fragmentation. Okay. We further assume that primarily we are concerned with external fragmentation. Okay. Primarily we only take a look at external fragmentation, I guess. Allocator could of course also have the problem of internal fragmentation. If an allocator hands out chunk of memory bigger than the requested, hands out chunk of memory bigger than that request, any unasked for and thus unused space in such a chunk is considered internal fragmentation, because the waste occurs inside the allocated unit. The waste occurs inside the allocated unit and is another example of space waste. Is that only the problem with internal fragmentation here? Only the space waste? I'm not sure. However, for the sake of simplicity and because it is more interesting of the two types of fragmentation, of the two types of fragmentation, we will mostly focus on external fragmentation, right? It looks like in this chapter we will focus on external fragmentation instead of internal fragmentation. Okay. We will also assume that once memory is handed out to a client, it cannot be relocated to another location in memory. Okay. This is the assumption for this chapter. we assume that once memory is handed out to a client, it cannot be relocated to another location in memory. I guess this is to make things simple. I assume, for example, if a program calls malloc and is given a pointer to some space within the heap, that memory region is essentially owned by the program and cannot be moved by the library until the program returns it via a corresponding call to free. Thus, no compaction of free space is possible, which would be useful to combat fragmentation. Okay, no compaction of free space is possible. Okay, right. Compaction mechanism can be expensive, I guess. So this assumption make things simple. Okay, fragmentation. Let me read the footnote first. Once you hand a pointer to a chunk of memory to a G program, it is generally difficult to determine a reference or pointer to that region, which may be stored in other variable or even in register at a given point in execution. This may not be the case in more strongly typed garbage collected language, which would thus enable compaction as a technique to combat fragmentation. Okay. Yeah, it is difficult to determine a reference to that region. Okay. Compaction could, however, be used in the operating system to deal with fragmentation when implementing segmentation, as discussed in said chapter on segmentation, which is chapter 16, right? Finally, we will assume that the allocator manages a contiguous region of byte. In some cases, an allocator could ask for that region to grow. For example, a user-level memory allocation library might call into the kernel to grow the heap via a system call such as sbrk when it runs out of space. However, for simplicity, we just assume that the region is a single fixed size throughout its life. Okay, let me list that, I guess, as some okay, wait. A basic interface. Using basic interface such as malloc and free, and then focus focus on external fragmentation. Okay. Instead of internal fragmentation, and then cannot relocate to another location in memory. Cannot relocate another location in memory. Okay. The region is a fixed size. What is it called? Region of memory is a single fixed size throughout the program lifetime. Something like this. Okay. So we have this assumption using basic interface, and then focus on external fragmentation, and then the memory cannot relocate to another location in memory, and then the region of memory, I think use, is a single fixed size throughout the program lifetime. Something like this. Okay. If I understand correctly, we have this for assumption. For chapter 17 here. Okay. Let's check this out. Low-level mechanism. Before delving into some policy detail, we will first cover some common mechanism used in MOS allocator. First, we will discuss the basic of splitting and coalescing common technique in MOS any allocator. Second, we will show how one can track the size of allocated region quickly with relative ease. Okay. Finally, we will discuss how to build a simple list inside the free space to keep track of what is free and what isn't. Oh, so okay. Inside free space. Interesting. Okay. The basic of splitting and coalescing. Okay, what is it called? Mechanism, I guess. Basic splitting and coalescing. Alright. Track the size of allocated region. The size of allocated regions quickly and with relative alternative is how to put a simple list inside the free space to keep track of what is free and what isn't free. Okay, maybe something like this. Alright, splitting and coalescing. A free list contains a set of elements that describe the free space still remaining in the heap. A free list contains a set of elements that describe the free space still remaining in the heap. Thus, assume the following 30-byte heap. Okay. The free list for this heap would have 2 elements on it. One entry describes the first 10-byte free segment. Okay, the free list for this heap would have 2 elements on it. This one and this one, right? One entry describes the first 10-byte free segment, byte 0 until 9, and one entry describes the other free segment, bytes 20 until 29. Okay. Is this the representation? Maybe. As described above, a request for anything greater than 10 bytes will fail or returning null. Okay. So we enter from this, and then this is the what is it called? This is the possible return value, I guess. And if it is greater than 10 bytes, we will returning null. There just isn't a single contiguous chunk of memory of that size available. A request for exactly that size, 10 bytes, could be satisfied easily by either of the free chunk. For exactly that size, 10 bytes, could be satisfied easily by either of the free chunk. But what happens if the request is for something smaller than 10 bytes? Okay, we already know what happens when we have the request greater than 10 bytes, which will return null, right? And what happens when we request the size exactly the size of the chunk, which is 10 bytes here. It will just give the, what is it called? The address of the chunk. But what happens if the request is something smaller than 10 bytes? That we haven't know yet, right? Assume we have a request for just a single byte of memory. In this case, the allocator will perform an action known as splitting. Okay. We have a request for just a single byte of memory. Oh, known as splitting. It will find a free chunk of memory that can satisfy the request and split it into two. The first chunk it will return to the color. The second chunk will remain on the list. Okay. So we split this, what is it called? This memory region, I guess. Okay. The list would end up looking like this. Right. 120. Okay. Where is it again? The second chunk will remain on the list. Thus, in our example above, if a request for 1 byte were made and the allocator decide to use the second of the two elements on the list to satisfy the request, the call to malloc would return 20, the address of 1 byte allocated region, and the list would end up looking like this, right? And that make me kind of curious. Why are we splitting this address, this memory region, and not this one? Is there any order when the allocator trying to split? Wait. The question is that, is there any specific order when we split when we decide to split the memory region? Like, how do we decide which memory region we should split? Maybe something like this. Yeah, how do we decide which memory region we should split? Okay. In the picture you can see the list basically stays intact. The only change is that the free region now start at 21st or 21 instead of 20, and the length of that free region is now just 9 power 3. Oh, this is the footnote. Okay, let me read the footnote first. This discussion assumes that there are no headers, an unrealistic but simplifying assumption we make for now. No headers. What headers in this mean? Yeah. I didn't know yet. Maybe the book we will talk about that later on. Let's see. The length of that free region is now just 9. Thus, the split is commonly used in allocator when requests are smaller than the size of any particular free chunk. A corollary mechanism found in many allocators is known as coalescing of free space. Take our example from above once more, free 10 bytes, use 10 bytes, and another free 10 bytes. Given this tiny heap, what happens when an application calls free 10, thus returning the space in the middle of the heap? If we simply add this free space back into our list without too much thinking, we might end up with a list that looks like this. Okay, this one. Okay, right. Oh, we haven't done splitting here in this figure, I guess, because the length in this case is still 10. Maybe we decide to take the address backward, I guess, from behind, and then let's say if we need another 10 bytes with this list, right, we might take this address first. Is that it? And then if we need another 10 byte, we will take this address. Yeah, I'm still not sure which order we take the free memory, I guess, from the list, from this free list. Not okay. Maybe let's split this question. How to with the set with memory again? We should split, and then we should decide to take free memory from free space, from free list. Maybe something like this. Right, okay. And then the second question is how to we decide which memory region we should split. Okay. Alright. Thus, if not the problem, while the entire heap is now free, it is seemingly divided into 3 chunks of 10 bytes each. Thus, if a user requests 20 bytes, a simple list traversal will not find such a free chunk and return failure. What allocators do in order to avoid this problem is coalesce free space when a chunk of memory is freed. The idea is simple. When returning a free chunk in memory, look carefully at the address of the chunk you are returning as well as the nearby chunk of free space. If the newly freed space sits right next to 1 or 2, as in this example, existing free chunk merge them into a single large free chunk. Thus, with coalescing, our final list should look like this. In this is what heap lists look like at first before any allocation were made. With coalescing, an allocator can better ensure that large free extents are available for the application. Now that make me curious. Let's say if we need, what is it called? We need 15, right? Oh, wait, maybe coalescing need to be a contiguous, what is it called? A contiguous region. Maybe the question is something like this. Do we need to have contiguous? Is that the word? Where is it? Okay. Okay. Contiguous chunk of memory to be able to do coalescing. Do we need to have contiguous chunk of memory to be able to do coalescing or combining contiguous, multiple contiguous chunk of memory to be able to coalescing this chunk of memory? Maybe something like this. Okay. Assume we have a okay. No, not that one. Indeed, this is what the heap list looked like at first, before any allocation were made. With coalescing, an allocator can better ensure that large free extents are available for the application. Oh, maybe this is why we have internal fragmentation. Oh, wait, it is not internal fragmentation, but it is external fragmentation. Yeah, because it happened externally, right? Yeah, this one, external fragmentation. Okay, so that is the external fragmentation example. The header used by malloc library, the 20 bytes return to the caller. Unallocated region plus header. Right, what is the header in here means? Specific contents of the header. Oh, if the header means the, what is it called? The information for the total of free space, maybe. Yeah, tracking the size of allocated region. Let me drink first. Don't forget to drink water. Okay. Tracking the size of allocated region. You may have noticed that the interface to free does not take a size parameter, right? Thus, it is assumed that given a pointer, the malloc library can quickly determine the size. Thus, it is assumed that given a pointer, the malloc library can quickly determine the size of the region of memory being freed and thus incorporate the space back into the free list. Interesting. To accomplish this task, most allocators store a little bit of extra information in a header block, which is kept in memory, usually just before the handed out chunk of memory. Oh, okay. Let's look at an example again, figure 17.1. This one, an allocated region plus header. So does that mean the header also a part of the allocated memory? I'm still not sure. But according to this figure, it looks like the header is outside of the allocated memory. But where do we store the header information? Okay. To accomplish this task, most allocator store a little bit of extra information in a header block which is kept in memory, usually just before the handed out chunk of memory. Let's look at an example again. Okay, in this example, we are examining an allocated block of size 20 byte pointed to by ptr. Imagine the user called malloc and store the result in ptr like this. ptr equal malloc, right? The header minimally contains the size of the allocated region, in this case 20. It may also contain additional pointers. Okay, the header minimally contains the size of the allocated region, in this case 20. It may also contain additional pointer to speed up the allocation, a magic number to provide additional integrity checking, and other information. Let's assume a simple header which contains the size of the region and a magic number like this. Okay. The header minimally contains the size of allocated region. Additional pointers to speed up the allocation. Okay, a magic number to provide additional integrity checking. I'm assuming integrity checking is something like what is it called? Some sort of protection, maybe. Okay, and other information. Let's assume a simple header which contains the size of the region and a magic number like this. Something like this. Okay. In the example above would look like what you see in figure 17.2 when the user call free PTR, the library then uses simple pointer arithmetic to figure out where the headers begin. The library then uses simple pointer arithmetic to figure out where the header begins. Okay. Header. Oh. Negative one. Alright. Wait. Does that mean... what is it called? The header size is the same size? Oh no, I mean, what is it called? This is a pointer, right? So, what is it again? So we subtract with the pointer size, something like that. Okay. After obtaining such a pointer to the header, the library can easily determine whether the magic number matches the expected value as sanity check, right? I think the magic number is some sort of protection here. Okay, and calculate the total size of the newly freed region with simple math. That is adding the size of the header to size of the region. Okay, from this data. Alright. Okay, and then another question is, do we store the header block, the info about memory allocated, such as size and magic number, maybe something like that. In the free list too. Yeah, where do we store the header block? For allocated memory. Okay, where do we store the header block for allocated memory? For allocated memory in the free list too. That is the question here. Okay. Note the small but critical detail in the last sentence. The size of the free region is the size of the header plus the size of the space allocated to the user. Okay, note the small but critical detail in the last sentence. The size of the free region is the size of the header plus the size of the space allocated to the user. Thus, when a user requests n bytes of memory, the library does not search for a free chunk of size n. Rather it searches for a free chunk of size n plus the size of the header. Okay. Yeah, does that mean the header is not in the free list, if it is not in the free list, oh, right, because it is contiguous. Okay, looks like the header block is not in the free list too. So when user requests and bytes of memory, the allocator does not search for free space, free chunk of size n, but it searches for free chunk of size n plus 1. Chunk of size n plus header size. And then when we try to free this memory allocation, we can subtract the pointer to read the header information. The header information is before the actual requested memory. In contiguous order, maybe. Can let me check. Okay, right, maybe something like this. So it is not saved in the free list, but it is contiguous with the actual request memory. So we can do a pointer arithmetic to get the header information. Okay, embedding a free list. Alright, maybe I will read this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.